Alright, in this video we begin transitioning from section 16.1 and 16.2 where we've discussed line integrals, okay, line integrals of vector fields specifically. And here is the notation for a line integral of a vector field, and here is the method of computation. And we can see the steps outlined for a line integral of a vector field, that you first need to parameterize the curve C given here in the notation. You need to parameterize that as a vector valued function in one variable. You then need to find the direction of motion of the curve C. You need to find the vector field at the points on the curve C, right? And then we need to compute this one-dimensional line integral by projecting the vector field F in the direction of motion of the curve by doing a dot product, and that will look at the component of the force in the direction of motion. Okay? And then you will compute the 1D integral. Okay, so that was section 16.2. Okay, so what we need to do in section 16.3 is to consider that same line integral. Okay, a line integral of a vector field along a curve. All right, but what we're going to add in section 16.3 here is we're going to add a requirement to the vector field, and the question is, what if the vector field F is actually the derivative of some function? Okay, and you'll recall from calculus 1 that if we were doing an integral from a to b, and the function that we were integrating, one moment please, pause for just a second. Alright, we're back. So we were trying to recall from calculus 1 what happened if we integrated a function, and that function that we were integrating, the integrand, what if that function was a derivative of some function? Okay, so the integrand is, in fact, the derivative of some function f of x. And we knew that there was this thing called the fundamental theorem of calculus that says that the answer to this integral is to evaluate the antiderivative of the integrand, which is that function that you can take the derivative of to get the integrand here. So that's f of x, and we need to evaluate from a to b. So that will be the antiderivative evaluated at b minus the antiderivative evaluated at a. So that is the same question we're going to ask in calculus 3 here. We're going to ask, what if the vector field that we are being asked to integrate, f dot the r prime, the derivative of the curve, what if that vector field is actually the derivative of some function? Okay, and here is the series of steps that will happen. Okay, so let's go through those steps now. Okay, so let's add a blank page. So again, we are considering a line integral of a vector field. Okay, so we're integrating from a to b along the curve. The vector field along the curve dotted with the direction vector of the curve dt. But the question is, if this vector field, okay, so this is section 16.3, what if this vector field is the derivative of some function v? Sometimes you'll see the derivative of the function phi. So in this case, if the vector field, f is a vector field, this function v or this function phi is a scalar function. This is a scalar function called a potential. a potential function. Okay? If there is a function v, or sometimes called phi, whose gradient of that function is the vector field, right? Then we say that that scalar function is a potential function. So watch what happens here if we substitute for this vector field. You substitute the fact that that vector field is the derivative of some function, okay, and that derivative will be evaluated along the curve, and then we will multiply by dot product it with the derivative of the curve r prime at t. Sorry, this color thing's getting maybe a bit annoying here. So we substitute for that function, the vector field, the gradient of some function, okay? And we need to go back to recall something called the chain rule, okay? And we have seen this quantity before, the gradient of phi along a curve r of t dot producted with r prime of t. If we were to multiply that function out, the gradient would be the derivative of the function phi with respect to x, phi with respect to y, if our function phi is a function of two variables. R prime at t is dx dt, r prime at t is dy dt. So there is the direction vector of the curve. And if we multiply by that dot product out, we'll get phi x, xt, plus phi y, yt, otherwise known as the derivative with respect to t according to the chain rule, the function phi evaluated along the curve t. Okay, so this is the fact that this is from the chain rule here, and we can now make a substitution for this dot product here, that it is the integral from a to b, the integral from a to b of the derivative of this function phi evaluated along the curve dt. And because we have the fundamental theorem of calculus, okay, from Calc 1, right, we can see that we're just integrating a function. Okay, this is a Calc 1 function, just being some function, fancy function for f of t. Okay, and when you differentiate an integral or integrated derivative, you get the function itself, phi, evaluated at r of t, evaluated at the two endpoints. Okay, so this tells us that we need to evaluate the potential function evaluated at r at t is equal to b minus the potential function evaluated at t is equal to a. Okay, and what we're seeing then is that this integral of the vector field along a curve C can be simply evaluated as the potential function at the endpoints subtracted, sometimes called a potential difference. Okay, so if you want to evaluate a vector field along a curve, all we need to do, right, if we have a curve, okay, here's your curve C, you have parameterized it. This might be in the xy plane, for example. Okay, and we're looking at a curve evaluated at some time t is equal to a to t is equal to b, and you can evaluate the curve at that point at t is equal to a to get a point p. You could evaluate the curve at time b to get another point q, right? And then if we have a vector field here, right, here's specifically the vector field along the curve. So here we have the vector field, and here we have the vector field along the curve, and here we have r prime at t. So if you wanted to evaluate the work as you're moving along this curve from t is equal to a to t is equal to b, all you really need to do is to come up with a potential function evaluated at the point P and a potential function evaluated at the point Q, right? And then we need to find a potential difference. Okay, so the potential at the far end minus the potential at the point that you started at, this potential difference is going to be the same as the work along the curve. So ends this introduction to the theoretical underpinnings of the fundamental theorem of line integrals.